This video is specifically going to look at the preparation and reaction of acid halides. So acid halides are the most reactive of the carboxylic acid derivatives. So how do you form something this reactive? Well, you have to use a great electrophile to be able to do it. So what it looks like is you start with your carboxylic acid and you react it with thionyl chloride to give your acid halide plus SO2 gas and then HCl. Now there's a couple things that drive this reaction forward, and when we work through the mechanism, which we'll do next, I'll kind of show you what those are. So interestingly, the carboxylic acid is actually going to act as the nucleophile in this reaction. This is possible because of how electrophilic the thionyl chloride is. The electrons move down here, and then the electrons from this pi bond will attack the sulfur, moving that up. So we got a pretty big molecule now. So this is the compound that we've got right now. The lone pair from the oxygen will move back down and kick off one of the chlorides since they're great leaving groups. So this will give us now that compound. All right, next step is to deprotonate this oxygen down here that has that hydrogen. So that's going to be done with the chloride that just got kicked off. So Cl minus comes in, deprotonate. So now we've got this. All right, let's see if you can see where this is going now. I'm close to a carboxylic acid. The only thing is that I have this sulfur group rather than a hydrogen there. So I need to replace this oxygen and sulfur group over here with the chloride because that is the derivative we're looking for, an acid halide. So this group here is a great leaving group. It's a really good leaving group. So what I'm going to do is I'm going to react my chloride in a nucleophilic attack. So now, I have this compound. So the lone pair from the oxygen will come back down and kick off that as the leaving group. So then I'm left with my acid chloride as the final product. Now something I want to point out here, and I'll go to the next page to show you because there's not quite enough room here. One of the things that also drives this reaction is apart from the acid chloride, I got this as my leaving group. Right? This was my leaving group. The electrons from this oxygen can move down to here and kick that chloride off. This gives me SO2 gas. Anytime a reaction is forming gas, it's going to drive that reaction forward because that gas leaves the system. So then I've lost a product, right? I know these aren't equilibrium arrows, but if you remember Le Chatelier's principle, anytime I'm losing a product, I'm going to keep pushing to form that product. So I'm continually losing SO2 gas, which is going to push the reaction towards the products and towards the formation of more acid halides. Okay, so that's how you form the acid halide. Now what about the reactions of them? Okay, one general reaction you'll see is nucleophilic acyl substitution. And this will work with a number of different nucleophiles on an acid chloride. Okay, so I have my acid chloride. I'll react this with a nucleophile. And I'll just do in general, because there's a number it could be, and I'll show you which ones it could be. Kick off that chloride, and I'm left with my new compound. Now this nucleophile could equal water, it could be an alcohol, either a primary, secondary, or tertiary amine. Any of those could be the nucleophile in this nucleophilic acyl substitution. Another reaction that the acid chlorides can go through is reduction. So in this reaction, my acid chloride will end up becoming a primary alcohol. So the mechanism for this is I'll have my acid chloride and I react with LaH, lithium aluminum hydride. So if you remember, it's just a source of H minus. So that will come in and attack as a nucleophile. And now I'm going to have a very common reaction that you keep seeing, or a common mechanistic step. I'll reform the carbonyl and kick off the chloride. That keeps happening, right? And you'll continue to see it happening. So now I've got an aldehyde. LaH comes in again. But now I don't have any good leaving groups, right? Just the R group and the two hydrogens. So I will protonate with an acid. To give me my primary alcohol. So that's the reduction reaction of the acid chloride. Now the final major reaction that you'll see with the acid chloride is the reaction with a Grignard. So in this example, I'm going to use the following Grignard. So in the first step, the Grignard will come in and be the nucleophile. I'll come back down, kick off the chloride, just like I did in the reduction, just like I did in the nucleophilic substitution. Now, at this point, you're saying, well, this is just the nucleophilic substitution. Yes, but Grignards are very good nucleophiles, much stronger than the ones I was looking at before, whether it's water, alcohol, or an amine. So it sees a carbonyl, and it will come in again. So my Grignard will attack again. So I'm going to get two substitutions, or two additions, onto here. And then I add in, water or acid here. To get my final product. and quench this. Okay, so what if you only want one addition, though? You don't want two additions to this, so you want to form a ketone rather than forming just an alkyl chain. You can't just do one addition of the nucleophile because some of the acid chlorides will react twice with the nucleophile and others won't react at all. You'll get a big mixture of products. The way you need to do it is use what's called the Gilman reagent. So the Gilman reagent reacts with the acid chloride, but not the ketone. So this will allow you to just form that ketone. So the Gilman reagent looks like is it's a copper bound to a lithium and then two R groups. The R group is what you're trying to add. So if I'm reacting my acid chloride here with a Gilman reagent that has two ethyl groups on it, what I'll end up getting as my product is this. So you can use the Gilman reagent to have only one addition to your acid chloride. Alright, the next video I'm going to go over the preparation and reactions of acid anhydrides.